Significance of a cusp or asymptote. Cusp. That's how I say it. So, we have some function f at x is equal to x plus 2 to the radical or root 3 squared. Okay, that's what this means up here. It says determine critical values. Well, critical values are when we're talking about either local minimum or maximums, or possibly a cusp or an asymptote or a hole in the graph. Okay, so a critical value is, well, when we're trying to find something that will be 0, and when we're talking about slopes, we know we always want the derivative of the function. Okay, that's how we're going to find critical values. We talk about the slopes of something. So our f at x, or we're going to find f prime x. We're going to use our chain rule for this. This is going to give us 2 over 3 x plus 2. When we subtract that, we're going to go to negative of a third, and the derivative of the inside of that is just 1, so it doesn't really change the function. When we go to simplify this, we're going to get 2 over, nope, not what I was looking for, thank you, 2 over 3 times the root of x plus 2, sorry, not the root, but the cubed root of x plus 2, because remember that was a radical of 1/3. Okay, so this is our derivative function. Now, it's important that you guys realize, take a look at this. If x is the value of -2, we're going to get an undetermined function. Okay, an error in your calculator, if you will. We'll have some number, or specifically 2, because it's always going to be 2 on top, divided by 0, which we cannot do. It does not exist, this idea here. Okay. So what we're going to talk about is, if you guys remember, back to limits, and we'll go in more depth in this a little later in the next lesson. But we're going to talk about approaching -2 from the left and approaching it from the right. Okay. So if you guys remember what we meant by that, we still have this equation. We're going to plug in values when we had x is 2. Think of it as the limit of x as it approaches -2 from the left. Okay, and what we have there is our 2 is equal to our equation being this. Now we're not going to plug it into the derivative function. Okay, but I just want you to think of this idea as x approaches 2 from the left, and when we had written it this way, as x approached -2 from the right, and same function, right? Remember we had talked about h 3 cubed root x plus 2. Okay. Now we have this function here, and as we approach it from the left, where is it? Here we go. As we approach -2 from the left, we're going to have some value infinitely smaller than -2. So think of it like a number like -2.00. Oh, I forgot I can't make zeros. Sorry. Think of it as a number like x is -0.01, or x is -0.0001. We're getting infinitely closer to x. So we want to be just smaller than -2. Okay, when we go about this question. So that's when x is approaching -2 from the left, and when x is approaching, in this case, -2 from the right. Well, when it approaches -2 from the right, it's a little bit greater than -2. So think of it like a number like 1.9, or x is equal to 1.999. So we're just a little bit bigger than -2. We can go through the process of plugging these values in, smaller and smaller values. What I want you to realize is after you plug those values in, so say you plugged in this for x, and you plugged in this for x here, what you would have found is some limit when x is approaching -2 from the right. You would have found that your answer will become positive. Okay, you're going to get some positive answer. And in this one, you're getting a limit when x approaches a negative 2 from the left, you're getting some answers that are negative. Okay? So we have negative answers in that case, as x approaches 2 from the left. Now what happens is those numbers, remember when we're solving limits, when we plug these numbers in, we actually don't approach the same number. Okay? In this case, we approached negative 2. In this case, when we approached it, we were coming up towards a number like negative 30. Okay? And in this case, we were coming towards a number like positive 30. Which means at the point 2 on the graph, these are not the same point. One is far away from the other one. Okay? So what we're going to do is we're going to bring up a graph to make sense of that. So I'm going to bring up a graph of the derivative first. So here's our equation. This is our derivative, the first function. So I put up a graph. If you notice, let me draw on top of this. Nope. I'm supposed to be able to draw on this. That's not happening. Oh well. If you notice what's happening is we're getting towards some type of asymptote on the derivative here. Okay? And what this function represents, they asked us to put it on our graphing calculator. They didn't actually ask us to graph it ourselves. So this is the original function. Our original function is some cusp. Okay? And at that point, the slope is undefined. We don't have a slope there. We have an undefined slope. So this is a critical value for us. Okay? This is very important because this is not a local maximum or minimum either. This point doesn't exist here. There is no slope at this point. Okay? So I want you guys to be aware of that when we talk about critical values, we could also be talking about local maximums, minimums, or essentially points that don't exist for us. Okay? In terms of like a limit. And in our next lesson, what we're going to end up doing is we're going to talk about approaching from the left at like negative infinity, a limit, and a limit approaching from the right at positive infinity. We're going to talk about how to put those into the equation. But I just wanted to get this idea in your head, that we can also get functions that don't exist here.